You open a streaming app, and it instantly surfaces a movie you end up loving. That moment of perfect prediction is powered by a SparseNN, a neural network architecture built specifically for recommendation at scale. The core problem? The system must understand you, one of hundreds of millions of users, and this specific item out of millions of choices. But user IDs and item IDs are just arbitrary labels, not numbers a network can reason about. In machine learning, we split inputs into two kinds: dense features and sparse features. Dense features are naturally numeric: watch time, hour of day, content rating. Sparse features are categorical: user ID, movie ID, genre tag. Dense features are easy. You hand them straight to a neural network. Sparse features are the hard part because a category like user number 4 million is just a label, not a number with meaningful magnitude. The naive fix is one-hot encoding. Create a vector as long as the number of possible categories, put a 1 in the slot for your category, and zeros everywhere else. But when you have millions of users, that vector is millions of entries long, almost entirely zeros. It's absurdly wasteful, and worse, it tells the network nothing about which users are similar to each other. The elegant solution is an embedding table, a learned lookup that maps each ID to a short, dense vector, typically dozens to hundreds of values. This is the heart of the SparseNN. Think of it like a library card catalog. You walk in with an ID number, flip to that entry, and pull out a compact personality profile the system has learned to associate with that ID. Concretely, the embedding table is just a matrix, rows indexed by category, columns are the learned dimensions. A lookup is simply selecting one row. This is what this equation captures. Here's the magic. These vectors are not hand-designed. They're learned from data. During training, the network nudges each embedding so that items that behave similarly end up with similar vectors. Visualize all your movie IDs scattered in embedding space. As training runs, the dots drift, comedies cluster together, action movies form their own neighborhood, horror settles elsewhere. The network discovered genre without ever being told what genre is. Users cluster the same way. Two users with completely different IDs but identical taste, same genres, same watch patterns, will drift toward the same region in embedding space. That proximity is what makes recommendations transferable. Now let's build the full SparseNN architecture. On the sparse side, every categorical feature, user ID, item ID, genre, device type gets its own dedicated embedding table, and a lookup produces a vector for each. On the dense side, all the numeric features, watch time, hour, content rating, are stacked into one vector and passed through a small neural network called the bottom MLP. This compresses and mixes them. These two streams, sparse embeddings and the dense output, then meet at an interaction layer. Here, every pair of vectors takes a dot product, measuring how compatible those two features are. A dot product between two embedding vectors is like a handshake that measures compatibility. When both vectors point in similar directions, the product is high, a strong signal of alignment. When they're unrelated, it's near zero. All those interaction scores get collected alongside the dense features, concatenated into one combined vector, and fed into a final network, the top MLP, which outputs a single score, the predicted probability that you'll click, watch, or buy. So why is it called sparse? The embedding tables can hold billions of parameters, one row per user, one per item. But for any single prediction, you only look up a handful of raws. The vast majority of the table is untouched. The access pattern is sparse. It's like a parking lot with a million spaces where only a few dozen cars show up on any given run. The lot is enormous, but usage is sparse, and that's a feature, not a bug, because it lets the model store rich knowledge about every individual user and item. At production scale, think Meta's DLRM or Google's recommendation stack. Embedding tables are so large they must be sharded across many machines. The sparse access pattern is exactly what makes that feasible. Each machine only needs to serve a fraction of the table on each request. Every design choice in a SparseNN is a direct answer to a real problem. One hot was too big and too dumb. Embeddings replaced it. Dense and sparse inputs needed different treatment. Two paths solved it. Pairwise compatibility mattered. Dot product interactions captured it. That's the design intuition behind one of the most widely deployed neural architectures in the world.